Hello everyone, this is Mr. Sorrentino again, and I'm doing this video for section 3.3 in our Math 31 course, which deals with analyzing the graphs of quadratic functions. We had looked at the graphs of quadratic functions before, and we talked about the fact that it was a parabola, which you see me emphasizing here. However, we haven't really, graphed them beyond, in more practical ways than what we had been doing beforehand, which was either just picking some x's and calculating what the y values are and just plotting the points and hoping that we get the center point or find out where it either bottoms out or tops off. Or we were using graph transformation techniques, which meant we had to start with a basic function and then apply those transformations to make it appear a certain way. Um, a lot of what we're going to learn today comes from the fact that we could do those transformations and it creates some certain summary information along the way to help us graph these a lot quicker so we get a better picture of the situation a lot faster, and also allows us to analyze certain situations where I want to maximize or minimize things where quadratics would come into play, because locating the vertex is going to help me do that, and it's pretty easy once you have it in a certain format. So the first thing that we talk about, there's two formats that we can easily graph quadratic functions, and we're going to talk about both of them. But generally, when I graph quadratic functions, I want to find the vertex first, because the vertex is that either highest point or lowest point, and that's where the main shape is coming from. And then what I want to do is determine the axis of symmetry. Now, we're not talking about the x or y axis and being symmetric about that. The axis of symmetry is a line that's going to pass through the parabola, which divides it exactly in half. Since we're talking about functions here, so basically one of the things we're going to talk about is that, well, for that to happen, it does have to pass through that vertex. So basically, me locating the axis of symmetry is something that lets me find where the vertex is. We want to determine whether there is a maximum or minimum value, and we're going to be able to know, because we want to be able to know if it's going to look like this, or is it going to look more like, this. That's important. And we want to be able to find additional points to graph of the function, but we want to be choosy about them so we can get an idea of what the picture looks like without having to graph too many points. So there's two types of quadratic functions to graph. And if you don't have it in one of these formats, the whole idea is to try to put it into one of these formats. One is a lot easier to put into than the other. The other one, if you're not given that format, it's better to just try to transform it into the other format. So let's look at these formats. The first one is what we call this format here, and this is sometimes known as vertex form or standard form. So this is type 1. And as you can see here, there's pictures along with it, and this is actually presented in your textbook, in your notes. F of x equals a times x minus h squared plus k. hk is the coordinates of the vertex. The a value in front tells me it opens up if it's greater than 0, it opens down if it's less than 0. Since the axis of symmetry has to pass through the vertex, x equals h is the axis of symmetry. And the k value is either going to be a minimum or maximum depending on which way it opens. So let's have a look and see how we can use this information to graph example 1. So organizing my information a little bit here, I can see that this is the a value, this is the h value, this is the k value. And I want to pay attention to that format. The format is f of x equals a times x minus h squared plus k. Because I want to make sure I know what the h and k values are and what a is. So a equals -2, which of course is less than 0. This tells me that the parabola opens down. If it opens down, it has a maximum. So, I know the general shape. The shape's going to look, like this in general. I know that h, following the structure, is 2. K is -3 because the k should be added. So this is like the -3 here is like having a plus -3. So that's what k has to be. So that means that my vertex is at 2, -3. Now on my graph, I have some information, and I also know my axis of symmetry is at x equals 2. So now, letting all of these grids be units of 1, 2, -3 would be here. And my axis of symmetry would be right here. I'm representing with a dashed line. It's not part of the graph. The only thing I have on the graph right now is that 2. And I know it's going to look like this, but I don't know how wide it's going to go, how thin it's going to be. So I needed to figure out some other points on the graph. Realizing that the vertex is kind of a central feature, and me already knowing what happens at 2, I can pick to either go on the right-hand side of that 2 or on the left-hand side of that 2, and realizing that since there's some symmetry here, I'm going to have some mirror images. So if I say I chose 3 for an x value, if I plug 3 into the function, if I do f of 3, I'm going to get this. Of course, 3 minus 2 is 1, square that is 1, times -2 is -2, -2 minus 3 is -5. So I have -5 here. So I can plot that. 3, -5 would be here. That's 1 unit to the right of the axis of symmetry, so there should be 1 at the same level on the left of it. It's mirror image. So every time I find 1 additional point, I'm actually finding a second. And I could do it for 1 more. Let's see what happens at 4. Might get a little bit out of hand, but if I do f of 4, I'm going to have -2 times 4 minus 2 squared minus 3. 4 minus 2 is 2, squared is 4, times -2 is -8, minus 3 is -11. And so 6, 7, 8, 9, 10. -11 would be about here, if I had to guess. And I'd have a mirror image over here as well. And so that gives me an idea of what the function should look like, what the parabola should look like. Just try to make them look as rounded as possible. You can see I'm not doing it perfectly either. Just don't make them look like a V. So there's a very accurate depiction of the graph based off of me analyzing information and choosing the right points to choose. I only really had to calculate 2 specific points to get like the idea of the shape. Everything else was given outright in the function. So that's when you have it in standard form, aka vertex form. There's another form that you're going to see for quadratic functions as well, and that's the next example. Type 2 looks a lot like things we saw in the previous lesson when I was solving quadratics. This is known as polynomial form, ax squared plus bx plus c. In some textbooks it's known as general form, and others it's even known as expanded form. When it's in this expanded form, I can still find the same information. It's just, how I express it differently. Now, first of all, I still have an a value, which, if it's greater than 0, means it's opening upward and has a minimum. And if it's opening downward, a is less than 0, and which means it's going to have a maximum. But the other thing that's different now, a is just the number in front of the x squared. So I use that to judge what's going on here. The axis of symmetry I can calculate by doing a formula -b over 2a. Notice that is like, that's looks like part of the quadratic formula, and it does have its origin from there, because if you're graphing a quadratic function and looking for what values a squared plus bx plus c could be, Well, remember again that I can have, most of the time, I'm going to have two different x values that are going to produce the same y value. Except, at the one place it doesn't happen is at the vertex. And if I'm solving a quadratic equation and it's set equal to a point that's going to be where the vertex is going to represent the answer, that's when I'm going to have that situation where I only have one solution that we talked about, and that's where basically your square root portion and the discriminant becomes 0. So that's represented with the vertex. And so if I do negative b over 2a, I can figure out where the vertex is. And if I know where the vertex is, well, I know where the axis of symmetry is, and I know that the vertex has to lie on that. And that's going to be the x coordinate of the vertex. I can figure out the y by plugging that number into the function and getting the y coordinate. So what I sounded sounded much more complicated than what it actually boils down to. So let's see it in action here. So I have the function negative 1/2 x squared plus 3x minus 2. So here's a, here's b, here's c. And so I know a in this equals negative 1/2, which is less than 0. So that means that this is going to open down. It's going to have a maximum. Now, here I'm going to find the axis of symmetry first. See, the other form, the reason why it's one of the reasons it's called the vertex form, it out and out gives you the vertex. This one here, it's more indirect. It does give me the axis of symmetry pretty easily. I'm going to figure out, okay, well, the axis of symmetry is going to be at the formula x equals negative b over 2a. Well, that's going to be negative 3 over 2 times negative 1/2, which is going to be negative 3 over negative 1, which is going to be 3. So I know the axis of symmetry is going to be here at x equals 3. So I'm just going to draw a dashed line there right now. And my vertex, so far, I have the coordinate 3 comma something. So if I do f of 3 to figure out what the y value is, I'm going to have negative 1/2 times 3 squared, which is 9, plus 3 times 3, which is 9, minus 2. That's going to give me 4.5 minus 2, which is 2.5. I think I was to say it's 5/2, but same thing. So at 3, 2.5, so 3, 2.5, which I'll say is right here, that's where my vertex is. Hopefully you're seeing it because the arrow's guiding and you see I'm making that spot rather big. So I have one point that's on this graph already. That's the vertex. So again, if x was 3, that's where my vertex was. Now again, I'm going to choose some values on one side or the other. I'm either going to choose some values that's smaller than 3 or those that are bigger than 3. If I choose 0, for instance, I always try to make sure to use 0 when I can because 0 is really easy for these. If I do f of 0, everywhere that there's an x, it will become 0. So negative 1/2 times 0 squared is 0. 3 times 0 is 0. So I'm going to have 0 plus 0 minus 2. That's a negative 2. So I know here it's going to be at negative 2. So 0, negative 2 is a point. That's 3 units to the left of the axis of symmetry. So 3 units to the right, I should have its mirror image. So again, every time I come up with one point for the parabola, I'm going to come out with a second point because it's just simply a mirror image. I'm going to choose 1 for another. Let's choose 2 because 2 will work with that negative 1/2. F of 2, well, negative 1/2 times 2 squared. Well, 2 squared is 4. Negative 1/2 times that is going to give me negative 2. Plus 3 times 2, which is 6, minus 2. Negative 2 plus 6 is 4. 4 minus 2 is 2. So 2, 2 is a point. So 2, 2. That's 1 unit to the left of the axis of symmetry, so 1 unit to the right should be its mirror image. And now you have enough to see what the graph kind of looks like. You can put more points in if you want, but I have enough right now to kind of know what it's going to look like and how wide it needs to be and so forth. Yeah, I'm looking for perfection here. Just make sure you indicate some points for accuracy. And having a table also lets me know that, what you intended to put in there. So, and of course 3 was at 2.5. I'll just put that in there just for the sake of argument. So there's my graph. Pretty easy and straightforward. So that works out pretty nicely. So you're just looking at again, it's just a little bit of analysis lets you figure out what you need to do. These functions can also help you do some situations where you want to maximize or minimize something. And that's where example 3 gets into. So let's have a look at example 3. Now, I had mentioned before, the quadratics, of course, are degree 2 equations. You have squares in them. Area is something that deals with square units, and most of the time you're going to see that situations dealing with areas can be written as quadratic functions and quadratic equations. So keep that in mind because, when I start dealing with area problems, I know it's going to be quadratic. And if I know I'm looking to maximize an area like I am here, you can see here it's saying maximize the area. If I want to maximize the area, I'm basically looking for the vertex of a parabola and what's going on here. I just have to make sure I'm accounting for the situation correctly. A rancher wants to build a fence to create a rectangular corral for his cattle. He has a total of 800 feet of fencing available to build the corral. What are the dimensions of the corral that would maximize the area of the corral? What is the area of that corral? So it's asking a couple of questions about it. So we want to build a rectangular corral. So I'm going to draw a rectangle. Now, if you remember some principles from geometry, and this was emphasized in your geometry course, you might already know the answer. It's pretty straightforward because there's a rule for this. Basically, it says if you're trying to maximize, if you want a rectangle that maximizes the area that has a certain perimeter, then it's going to be a certain shape. It's going to have certain dimensions. And I'm not going to get into that and give away the ending right now, but if you know that rule, that's also acceptable. We have 800 feet of fencing, which means the perimeter of this has to be 800 feet. I'm assuming I'm using all 800 feet of this fencing with not anything left over, So, I have, a length, a width, a length, a width, and that the perimeter is 2 lengths plus 2 widths. That should total 800. The problem with that is I'm dealing with 2 variables here. Because ultimately, it's the area I'm looking to maximize here. The area formula is what's important here. And that's length times width. I can't really, graph things with 2 different variables. The graphs we do puts one variable, which would be the area, in terms of one other variable. Well, which other variable am I going to use here? If I have 2 different variables there, I really can't graph this. I would need to have an a-axis, an l-axis, and a w-axis. That'd be a 3-dimensional graph, which is kind of hard to do on a 2-dimensional surface. Or you'd have to try to find a way of erecting one and then try to find a maximum from that. That's not easily done. 3-dimensional models are not easy to do unless you have some pretty sophisticated computer equipment. We want to make this easy so that we could possibly do things on the calculator if worst came to worst, which would graph a 2-dimensional graph, or just use some basic algebra. So I want to get this in terms of one variable. That's why the perimeter information was important, because I could take this and say, well, 2L equals 800 minus 2W, and dividing both sides by 2, L would be 400 minus W. So instead of having these written as L, I can just say this is 400 minus W, and this is 400 minus W. So now my formula for the area is 400 minus W times W, which is negative W squared plus 400W, which is a quadratic function. Doesn't have a C value, which is okay. But, if I'm going with my terminology, this negative 1 here is A, 400 here is B, and of course C is going to equal nothing. So I have a formula for this. I want to find, what are the dimensions and what's the maximum area. Okay, so, well, if I think about this, I have a graph, and this is obviously a graph that has a negative A value here. If I was to graph this, I would see something along the lines of this. I know it's opening downward because the leading coefficient, A, is negative. The maximum would occur at the vertex. So if I can locate that vertex, I'm going to be able to locate, this is my L, this is my W, this is my area, instead of taking the place of the X and the Y. The vertex is going to give me the W value that I need and the area, which is the max area. So if I find the vertex, I'm going to have both parts of what I need to come up with an answer. So let's figure out where this goes. Now this is in the expanded form, so I know that the axis of symmetry is going to be at W equals negative B, which is 400, over 2 times negative 1, which gives me negative 400 over negative 2. It's going to be at 200. The width would have to be 200 for this to happen. Now I can plug this into the function and get an answer, but I can also think what's going on here. If this is 200, that means that this length, which is 400 minus W, is also going to be 400 minus 200, which is 200. So the dimensions are 200 feet by 200 feet. The maximum area well, I could either plug 200 into the area function and get it, or realize that, well, if I have both dimensions, 200 times 200 is going to be 4 and 4 zeros. It's going to be 40,000 square feet. So there's the answer, and that kind of goes back to the geometry concept that if I have a rectangle with a specific perimeter, the maximum area that I could get with that rectangle would occur when that rectangle is actually a square. So, that principle could be applied here if you happen to remember it. Otherwise I show you the algebra here. And it's important to know this algebra because we're going to look at a situation now that's going to make things a little bit different. So, same rancher, 800 feet of fencing, wants to build a corral, except now he's going to build it against his barn. And we're assuming the barn's going to be have a sufficient length to, have no opening on the one side. So basically what's going on here, in this instance, I'm going to have a barn right here. My fencing for the corral is going to be here. So what I have here is I'm going to have these two, I'm just going to call them X in this instance. Opposite sides should be the same. And obviously, this should total the perimeter, the fencing perimeter should still be 800 feet of fencing. So if this, and if this, and what's missing down here should total 800, it stands to reason that this should be 800 minus 2x. I'm trying to find a way of only getting one variable involved so I can, create a situation that can be graphed and that any analysis I would do would be able to, figure out where the vertex would be and so forth and so on. So, so I kind of use the same principle that, the three sides that I'm now building should total 800. Two of them are the same measurement, so 800 minus the total of those two sides is going to be what the third one is. And so my area for this is going to be, well, this is the one dimension, this is the other dimension, so it's going to be x times 800 minus 2x. And so now when I carry through the multiplication and expand it, I'm going to have negative 2x squared plus 800x. And so this is the formula that represents, every possible area I can get from 800 feet of fencing, and I want to find which one's going to have a maximum area. Where's the area going to be the largest? And that's going to happen at the axis of symmetry. So my axis of symmetry is going to happen when x equals negative b over 2a, which is going to give me basically 800, negative 800 over negative 4, which is 200. So this is going to be 200 feet, and this is going to be 200 feet. This side here, 800 minus 2 times 200 is going to be 400 feet. So I have the information I need now, because again I'm asking for right now I'm just looking for what would the maximum area be. I should say B, not he. To enclose this. So basically, we're not looking so much for the dimensions, although I know what they are now, but the maximum area, either by plugging the 200 back into this function here, or just simply saying, okay, well that's going to be the 200 times the 400, that's going to be 80,000 square feet. Because when I'm looking for a maximum, or in some cases you might see I'm even looking for a minimum, when I'm looking for a maximum, I'm looking for a vertex. I'm not solving for a specific instance. I'm searching for an instance where I have the maximum possible area. And that's the end of the examples I have here. You're going to get a chance to try some on your own, so make sure that you do give them a try. And if you have any questions with anything here or any of those questions, please make sure to bring them up in class or see me during my office hours. Until I see you in one of those places or until the next video, I'll see you around. Have a good day, everybody.